Well, let's begin. This is Professor Tahmineh Azizi from the University of Wisconsin-Madison. And I was intrigued by her offer to talk about using fractal geometry. Oftentimes, fractal geometry is just something that you use maybe for pleasure to look at and say, ooh, is that beautiful? But this is in the service of nature. So I turn it over to you, and I'll give you a 5-minute warning when we're close to the end. But other than that, you're on. Thank you.
That's awesome. Thank you so much for the introduction. Thank you so much, Dr. Winkler, for organizing this conference. It's virtual. I'm very happy I cannot travel, so it's good for us to gather all of this researchers from everywhere, teachers, and I'm excited to be here. I attended last year. I really liked this conference, so I decided to attend this year, and I'm happy that my talk got selected. So thank you so much, Dr. Winkler. And this year I selected a different topic, so it's for undergraduate research and modeling. Maybe before even studying fractals, I didn't know that people, they use fractals to model different objects, different phenomena in nature, even inside bodies. So that's why it was my topic for this year, how we can use fractals to model. And actually, I had one undergraduate student last year who was interested. We applied this fractal geometry on climate data. And she was not a mathematician, she was in urban planning. So she knew climate, she knew all of this stuff, but fractal was interesting for her. So I thought that maybe this is going to be a very interesting topic, not only for mathematicians, but also for non-math students and teachers. They can consider this topic for their students. So let's just start by introducing fractals. Maybe everyone knows that from high school, when they were teaching us about the fractals, and a fractal is a never-ending pattern. And these complex patterns, they are just repeating like infinite times. And the most important property of fractals, maybe you can see my mouse, is self-similarity across different scales. So if you just see the object from different scales, we see this object is repeating like in different scales. We have the same picture at different scales, and this is a very beautiful property and the main property of fractals. So they look similar at different scales. And fractal actually introduced for the first time this term as like fractal by Mandelbrot. His amazing masterpiece, I would say in 1980s, 1970s, he introduced fractals like at this name. But of course, fractals was discovered by another scientist, mathematician, Julia, very before, I'm going to say that, but not under this name. So Mandelbrot introduced fractal to us, and we are using now fractal geometry as a field in mathematics, and many students in analysis, they like it, and they studied specifically fractal geometry. And these objects are usually, we say they are irregular. They don't have a regular pattern, and we can see them everywhere. I'm going to show you different examples that you can show to your students. So actually, maybe we think that this is like just a simple mathematical like formulation. Usually we saw that, for example, Julia said how it's created. But this is just exactly how it is in mathematics. We have fractals as only like model for phenomena, for anything around, we see everywhere. And we can use a model, just a model for discovering the properties of these objects. So for example, clouds, mountains, coastline, and many other examples, they follow a fractal pattern. So they have the same property. And so as I said, yes, fractals, this name was introduced by Mandelbrot by Julia, who was the first mathematician who discovered fractals, but not under this name. So the first fractals was discovered by a French mathematician, and very before, we didn't have computer graphic to show like this beautiful design to our students. But Mandelbrot introduced fractals in this way. With this, we call this fractal as Mandelbrot fractal. And there is a course in undergraduate studies. Usually we learn like better than high school in undergraduate level, dynamical system, and they introduce us just very few things about the fractals and how what are the main properties of these objects, mathematical objects. And so one of them is they introduce us this is self-similarity, and the other one is chaotic somehow. But what does that mean? Self-similarity means that when you magnify the object, the fractal that you have, you see that object over and over again in its parts. And what does chaotic mean? So I don't want to go with analytical like definition of chaos, but just because they are infinitely complex, they call them like they are also chaotic. And these objects, they just they have a very simple mathematical process to create, and they can model many different like objects around, like in nature we see them. And I will provide some example, but let's learn more about self-similarity, which is a concept that in the theory of fractals. Maybe I go faster. So we say the phenomena is self-similar, means that this is the like same. This object has the same behavior in different scales. A scale can be like time or can be a space. And so coastline, we have like one example that people are trying, even actually there are some beautiful maps or coastline, they're trying to find the complexity of the coastline, talk about this like fractal properties in nature. And we can see like in geometry, like self-similarity, we can say fern or spiral or binary tree. There are different examples in geometry, students, they learn. And in nature, the fractal that we have in nature, they don't exhibit self-similarity over all times. And finally, like it's gonna break like down and it's not gonna continue. So this is one example in dynamical system. Students, when they took this course, they are familiar with this logistic map, this simple this discrete time model, and this branching diagram, they call it bifurcation diagram. And they saw in this course that yes, they have a copy of a bifurcation diagram in each. If they zoom more and more in any part of this, they can see exactly a copy of the bifurcation diagram and like different scale when they zoom more. So it's like again self-similarity. Or maybe you can see in this beautiful fractal objects here, when we continue zooming more and more, as you see here, we see the same thing over and over again. It's repeating. So it's self-similarity, the main property of fractal. And this is the Mandelbrot set that he discovered this beautiful, amazing like object and fractal. So, but actually there is a very simple mathematical formulation for all of this. You see very complex pattern you see here. But so we start when I was actually teaching to my student last year about the fractal. So there are some maybe measures like that they need to learn to when they want to analyze a fractal object, when they want to have like they want to work with data and model data. So the most important thing is finding the there is index for like complexity for when we talk about an object like a fractal, we want to say, for example, how complex is this object? Like they call this index as a fractal like dimension or like a complexity index to describe different objects that we have. But one of these actually dimensions or measures in fractal geometry, which is widely used by different, especially in engineering major people, they use it, called box counting dimension. As you see this, for example, you look at this map here and covered by these squares. Usually they use this square, this box, that's why they call it box counting. And they change the scale of this square to finally, they find using this formula a number which is not changing anymore after some times. And they call this number or this complexity index as a fractal dimension. So this is how maybe if you give a map like to someone who knows familiar with this box counting method, can find the complexity, can measure the complexity of this map. I don't know exactly where is it actually. So there are two, maybe even before undergrad, I didn't know that we can have fractal or multi-fractal. There are not only fractals in nature, and when we cannot use the fractal model to explain the complexity of the objects, we definitely cannot use fractals to model that object, and we need to have more complicated model, which is called actually multi-fractal. So we get like a spectrum of index, complexity index, and there is not only one index to explain that phenomena, that object. So fractal analysis is good for those phenomena which are like the distribution of that object is homogeneous, not heterogeneous. There are many examples that definitely fractals are not able to describe that object. So we go over other theory in fractal geometry they call multi-fractal analysis. And yeah, that's beautiful. That even I'm going to show some example. They find a model beautifully. They can model that complicated like behavior phenomena object with just using very simple quadratic model, and they can talk about the behavior of that phenomena. So sometimes when we don't have a fractal object, we need to talk about the multi-fractal properties. That object is not fractal, it's multi-fractal. Maybe I just go faster to show you some example to make it more interesting maybe for students when you want to introduce fractals. Yes, fractals are everywhere. I'm gonna start with very simple examples. Students usually in engineering, they learn about the nature of different surfaces that we see around. For example, this is actually one example of that. The students, mechanical engineering student, she was working on this. She wanted really to see how she can model the surface and the this complicated like surface pattern that this object has. Is there any way? Is there any formula? Is there any way we can do that? Yes. So this type, for example, surfaces, they easily can be modeled using fractal geometry. And as you see in the top part of this slide, we have a linear model which is showing the fractal properties of all of these 8 different surfaces, and we have a quadratic actually model. And this quadratic model is more exact to talk about the properties, everything about this object, because definitely when we look at this this quadratic nonlinear model is going to say more about the complex dynamic of this surfaces here, and we can use for a model, or even different, like maybe these are just generated by a computer. I use this also example to show my student, yes, there are different surfaces that just these are not real surfaces, but we can model them, how this surface behaves. We can easily catch using the fractal geometry and this quadratic model. But how about let's go inside of body and talk about maybe fractal geometry of brain, which is one of the most, I should say, it's the most complicated part of the body, brain. Actually, I'm working on brain data already, but we can use fractal geometry to model the different brain disease. One of them is, for example, Alzheimer. Alzheimer is very sad that is happening a lot inside of the country, and we see that through this disease, the white matter of the brain is shrinking. So this is interesting that students, they can learn, they can like conduct some research to understand how they can use fractal geometry to model these changes that happen inside of the white matter of the brain. It's really interesting. This is like a biomarker for clinical application, and they can really understand different stages of Alzheimer's disease. So during Alzheimer, we have really, it's very sad. It's very, for example, I'm going to show you some data. We noticed that when we use the fractal geometry, we can easily find out different stages of this disease just using the index. For example, it was a data for 2011, 2015 of the same patient. And so during Alzheimer, we expect to see some changes in white matter that happens. And yes, using this fractal geometry and this like quadratic form model, we could model exactly the changes, this alteration that happen in white matter of brain. And actually, we can, in the right-hand side, this box counting algorithm was just that I showed you that the formula for that can be used to find the complexity index for different stages of disease. So it's very easy for a student. They can apply this for learning more about different or even different brain disease, like we have Parkinson, or when like patient, this is very sad for all of this disease. Finally, some of them like the patient is gonna die, and some of them patient like has problem with moving, and many other like symptoms and many other things that happen during this disease. And again, we use we can use fractal geometry using this data that we have for example, for Parkinson or other type of disease to model them. And exactly, we can characterize different like disease, like brain disease. We had like 3 different brain, like Hodgkinson, like Parkinson. I'm not familiar with that much with this type disease, but using our tool, which is very simple in fractal geometry, we can easily characterize different disease. And heart rate as another example inside of the body. I think I have time, so I can go over that. So we have different heart disease also, and it is actually discovered like I think 20 years ago that the heart rhythm of a normal person is following multifractal behavior. And we can use this multifractal model to easily catch the behavior of a normal person. But when any type of like heart disease happens, like arrhythmia, maybe I show you the next slide. Like one of these diseases, arrhythmia, when it happens, this multifractal model cannot be a good model for those type of disease. But for the control one, as you see here, this is a control, the normal person. We could easily model the heart rhythm of this normal person, the control one, using the fractal geometry, and it's really multifractal. But when any type of disease happens, is this patient, the heart rate of this patient is going to lose the multifractal properties. It would be just a fractal, not that much complicated. And this is exactly a measure, a complexity index that can be used as a biomarker to recognize, to diagnose like different disease that happen, as you see in brain or heart, or people are working in this area a lot. And maybe different type of heart disease that they notice that really we can use this fractal geometry as a model to cover all of these changes that happened. As you see, there's sudden changes that happen in the heart rate of different disease, and we can use this fractal geometry to model this. But how about climate data? I just selected so many examples to just show, yes, it's applicable. Many places you can, when you have a data, for example, temperature data, we had some temperature for different part of the year, like October, July, April, and sometimes in this month, we had this data, and we were interested to see. I had a student, and she was interested to see if she can really model this data. This is really this, if you look at this time series data that we have, is just very noisy, there are so many sudden changes happen, like different scale of this data. So I was helping her to learn about this theory, like fractal geometry, and she could model And she was really impressed by how she could model this time series just using this simple quadratic model. Yeah, it's possible that we can use easily fractal geometry for climate data. And as you see, these all of these curves here, these quadratic curves, these are for different part of the year. So we could actually we could use them for classify our data. But there are so many machine learning techniques that this is nowadays people they use to for classification. But fractal geometry in mathematics can also do that for us, can also classify the data that we had. So far, we could use fractal geometry for classification as well. For example, this is another example like climate data. Yeah, I have still time. So how about also she was this is she was also interested about drought and can we like classify different stages that happen during drought. So we have I put them here, like we have maybe abnormal drought, like we have moderate, we have severe or extreme and very exceptional level for drought. So, and these are like different data that we had for just from 2000 to 2021. We had this data and for entire USA for this years. And she was interested to see if she doesn't want to use machine learning technique, can she use this fractal geometry to classify different levels of drought? As you see here, also in this map, you can see different levels of drought, like this darkest is going to be really the highest level of drought. And we have some very few. If you look at this map, it was actually very sad that we could see the drought is like sometimes it's really getting bigger, this darker place. But we could actually, using all of this historical data that we had, we could easily apply our method to classify, to model and classify, and we could really find a model that could describe the behavior of this drought. And what is the purpose of modeling is good because we want to see, we really don't know when it's going to happen drought, right? So the good thing about modeling is if you have the model, you can predict the future. We don't want to have drought, right? So this fractal geometry is going to give us not only a like complexity index to characterize different level of drought, it's going to also tell us, yes, using this model, you can definitely, and using the historical data, you can have a model that predict for the future, what is going to happen. And this is going to happen just using this fractal geometry. As I said, we can have a complexity index for characterizing different level of drought. To characterize them, we have like different levels, and we can also model using this quadratic model and talk about the behavior and what is going to happen in the future. So
we've got about 5 more minutes. We're doing time.
Oh, maybe I was so fast. So yes, this is a masterpiece of Mandelbrot that who introduced fractals to us, and now we are applying in different places. As you see inside of the body, outside body, like using climate data and everywhere. And this is, I would say, since we are using the rigorous mathematical techniques, is something robust also and stable, can be used really for modeling and introducing to our students. Thank you so much for your attention. Sorry if I was so fast to explain all of the examples, but I can repeat any part which was not clear. Thank you so much, Dr. Winker, for organizing, and all of the organizers of this amazing conference. And I'm happy for the second time to be here and talk about a very simple research for undergraduate students. Thank you.
Well, thank you very much. Any questions or oohs and ahs about these pictures?
I should look at the chat. I didn't look at the chat.
Yeah, Abdi.
Hi, great talk, really fascinating. Thank you. I have a couple of questions. One is, are you categorizing these fractals by their dimensions? Is that what those, I think those graphs were kind of, they had dimensions on each side?
Yeah, for example, here, yes, this one, right?
Okay. So
yes.
My next question on that is, have you used topological, like, Hausdorff dimensions and all that stuff in your studies, or?
Oh, that's a good question. Thank you for your question. Actually, for some of the examples, it's proved that they found the Hausdorff dimension and this box counting dimension, or they found for some examples they are equal. But in application, this is really hard to use the Hausdorff dimension for like finding this complexity index. That's why in many examples, I have seen people, they use box counting, for example, for images, those maps, but there are other techniques that I haven't seen any study that they compared with the Hausdorff dimension or not. For example, this heart rates or very noisy data that I showed, or many examples in application, as I have seen, for example, there are different algorithms. Higochi has one algorithm, like a dimension, specifically to find the fractal dimension. Yet there are different fractal dimensions. Some of the fractals, they have noun. For example, we have noun dimension for some of the famous fractals, which are, Hausdorff is analytical definition, which is very hard in application to use that. But some examples, they have seen that they are equal with the dimension that people usually they use in application, but some of them no. And it's very hard actually to apply Hausdorff dimension.
Right. So I just have a couple quick ones, and I'm interested in your work. Have you published any of this stuff?
Yes, not this climate data. Still, we are working with a student. She is really interested. We had some few data like for this. Maybe we want to develop is the data we had for USA. We want to see really, can we talk about other drought, other places? So our method was applied for this. We could really classify, we could model, but yes.
Right. Sorry, yeah. If you have your email address, maybe I can ask you more questions in detail. But
Yes.
I'm also interested in calculating dimensions of iterated function systems, the IFS type.
Of course,
And,
yes. Of course, yes.
And my last question is, those multifractals, I think there was some comment by Mandelbrot about them in relation to the stock market, if I'm not mistaken.
I have seen actually, yeah, I didn't have data for stock market. Yes, actually the multifractal analysis is good because we are using wavelet method. That's the stock market, the type of model that we can use. Wavelet can handle that, all of those type data. For example, even the other type data, I don't have it here. We have seen that with using this multifractal analysis, which is based on wavelet analysis, we can easily model the data. Yes, actually, is a good example if we apply there. Definitely, yes.
Thank you. Thank you so much. I don't want to take up anymore. Just like to communicate with you by email.
Thank you for the question. Thank you for the comment. Thank you.
So I have a question about practitioners. So you have these models of Alzheimer's disease and so forth. Are there reports of users like medical professionals or geologists or whoever, or climatologists, who look at these images and see something that they could not otherwise see, that it enables them to better understand? Are there maybe layman reports or, not too complicated descriptions of that somewhere?
Yeah, exactly. Actually, Alzheimer and Parkinson, these two type diseases, I have seen many published papers in Nature, and people, they notice that during different stages of, for example, Alzheimer, we have reducing the fractal dimension. And it was a good sign for all of this. It were actually using on like brain of maltreated children. It's applied there. I applied and I noticed, yes, we have reducing the complexity, which is consistent with all of these published results that we have everywhere. Yeah.
Okay.
Thanks for the question.
Because it allows the mathematician to interact with the medical and the practitioners in a way of helping them, visualize what's going on, and vice versa.
Yeah, that's why I'm in medical school, actually.
Yeah. Well, are there any other questions? If not,
I have one, Brian, if we have a moment.
Yes, sure.
With these graphs, when it's linear, if I understand correctly, the slope of the linear line is the Hausdorff dimension. It's the fractal dimension. When you have the quadratic, what is it in the quadratic that corresponds to the multifractal dimension?
Yes, thank you so much for your question. So for this linear one, I have only one exponent, which is describing this like object, this homogeneous object, for example, distribution. But for this, I get like a spectrum of this exponent. So I have like, I obtain all of this, I calculate them like for the object or data that I have, and it gives me the quadratic model. So this is how multifractal analysis works. So I have a spectrum of this exponent, not only one. And definitely the phenomena, the object should be really complicated, then we can apply it. And usually the support of this like multifractal spectrum is gonna give us like, if this is like just fractal or monofractal, or this is a multifractal phenomenon. When it is wider, it's a multifractal, is a sign of that.
Okay, thank you.
Thank you so much for your question.
All right, we need to close this. Thank you very much, Tahmineh, and we wish you well up north where it's cooler than Florida. And not only enjoy your pictures, but other things.